session. So we will be doing the final session of friction today. So in the last lecture, we had discussed about the two block problems in friction. So let's review that with an example, a similar type. Now difference is this time, let's take a situation where we apply the force on the block on top rather than applying it on the one below. Okay. So given mass of the block A is 10 kilograms, mass of the block B is 15 kilograms, and the coefficient of friction is 0.3. Okay. So we have to first of all find the accelerations of the block. Okay, so we want to find the maximum force we can apply to A such that there is no slipping between A and B. Okay, so let's start with this question. Try this out, people. So just apply the similar method that we discussed in the previous lecture. That given a certain amount of force, you start with an assumption that there is no slipping between A and B, and calculate the common acceleration by making combined free body diagram. But then also from the single free body diagrams, find out how much friction is required for that common acceleration between A and B. And check that friction against the limiting friction available. So from that, you know whether it will be possible for friction to prevent the slipping or whether there will be slipping taking place. So use that common method. Okay, so I'm just putting up the answers first, then we'll go through the discussion of this. So in this part, you will get the acceleration of A equal to the acceleration of B. They will have common acceleration of 1 meter per second square. Okay. And static friction of 15 newtons will act between them. In this part, you will have different accelerations. Acceleration of E will become 4.5 meters per second square, whereas acceleration of B will be 2 meters per second square with a kinetic friction of 30 newtons acting. And the answer to this part should be maximum force you can apply is 50 newtons for no slipping. Yeah, Prince, to answer your question, when we say acceleration from the ground means acceleration with respect to ground frame. Okay. So when nothing is mentioned about which frame the acceleration is measured from, we always assume it is the ground frame. So here, for example, in this question, if they are just asking what is the acceleration of the block, so we have to assume that they are asking with respect to ground frame. The default frame we take is always a ground frame. Okay, now just try to work out, whether you're getting these answers or something else and verify it. We will discuss the method next. Okay, so let's discuss about the solution of this question. Okay, so first part, when you are applying a force of 25 newtons, what we can do is we can start with the assumption that there is no slipping. Acceleration of A is equal to acceleration of B is equal to some common acceleration A, suppose. So first of all, make a combined free body diagram. And for that combined free body diagram, you will see there is only one external force acting horizontally, giving the system this common acceleration. So we should have F is equal to total mass into E. So our acceleration will come out to be the force of 25 newtons divided by the combined mass of 10 plus 15 kg. So it will come out to be 1 meter per second square. Now we want to check friction in this case. Okay. So for that, you make the individual free body diagrams and you understand that there should be static friction here because there's no slipping between A and B. So the type of friction here should be static. Now both these blocks should be having the same acceleration. And of course, the vertical forces, see here like this. So this static friction is generated by this normal reaction between A and B. So you can see that N1, which is the weight of this block, is equal to how much? This is 10 kg, so 100 newtons. N2 will of course become N1 plus weight, but that's not really important because there's no friction on the ground. So N1 is the one which is more important. So the maximum friction available to us is mu N1, which will become 30 newtons because mu was 0.3. Okay. So given this information now, we can see now for assuming acceleration of A is equal to acceleration of B, we got the common acceleration to be 1 meter per second square. So from B's free body diagram, you can see that this is the amount of friction that is required now. So for this friction required, we can see for this amount of friction required, we can see that the value is coming out to be 15 into 1 or 15 newtons only. Now check this against the maximum friction that is available. This much friction is needed, whereas this much friction is available. This is the maximum friction available. So immediately you can see that yes, the assumption is correct. Okay. So therefore, for F equal to 25 newtons, our assumption is correct. There is no slipping between A and B. Okay. So note this down if you haven't done this, and apply the same thing now for the second part. And in the second part, you'll be able to figure out that the assumption is actually failing, that if you assume they have common acceleration, that will not be taking place. In fact, they will be having different accelerations because the required friction will exceed the maximum friction available, which is 30 newtons. So you just have to repeat this whole thing, but with the value of force increased to 75 newtons in the second part. And you'll see the moment that happens, you will not have enough friction to support the common acceleration. Okay, so as you can see, what will be happening here is that in the second part, when we increase the force to 75 newtons, okay, assuming no slipping, okay, you make the combined free body diagram. You'll get this acceleration as 75 upon combined mass. Get it as 3 meters per second square. Now you make the free body diagram of the individual blocks. So more importantly for B, there'll be friction like this. We're applying the force to A. So for B, you can see the friction required is 15 kg into 3, 45 newtons. Now the moment you look at this value of 45 newtons, you know that this is not possible because maximum static friction available for us was mu n1, which was only equal to 30 newtons. So therefore, the maximum static friction available cannot prevent slipping when F is equal to 75 newtons. So once we know that this assumption has failed, next what we have to do, we have to change our assumption and go back to this equation that acceleration of A will be different from acceleration of B and the friction acting will be kinetic friction. Instead of static friction, it will be kinetic friction. So its value will be mu n1. So you go back to the making a fresh set of free body diagrams, and you cannot make a combined free body diagram anymore because they have different accelerations. So on this, there is this and kinetic friction. On this, there is kinetic friction. This will have a different acceleration. This will have a different acceleration. So for E, we will have capital F minus kinetic friction is mass into acceleration. So we'll have 75 minus 30 is equal to 10 times acceleration of A. So we'll get this value as 4.5 meters per second square. And for B, so these will become the accelerations in this case. Okay, so this question, this part also itself gives you a hint about, the maximum force you can apply. It gives in the hint in the sense that third part, when you want to calculate maximum force for no slipping, you can already understand that since maximum friction available is mu n1, which is 30 newtons. Okay. Therefore, you can also see that acceleration of B's maximum possible value is maximum friction divided by mass of B. Okay, because it's very simple that on the block B, there's only one horizontal force which is acting. So the acceleration of B in general is static friction divided by mass of B, assuming no slipping. Okay. So this tells us that it can have a maximum acceleration of only 2 meters per second square. Whatever value of F we apply, acceleration of B can never exceed 2 meters per second square for any possible force that we are applying on E. Okay. So for acceleration of E equal to acceleration of B, that is no slipping, okay, maximum value of this common acceleration is 2 meters per second square. Therefore, maximum value of force will be this. So this is the simple thing of calculating the maximum force so that there is no slipping. Okay, so that was that question. Now next we'll discuss another very important example. So we have a block placed like this on a rough surface, initially at rest. Okay. Now what we want to do is we want to make the block move by applying some kind of external force, and we are free to choose any angle theta with respect to the horizontal for that force, whereas the coefficient of friction is given to us as something, let's say, is given to us in this particular case as it says given as 0.75, suppose. Okay. So given mass of the block is, say, 20 kilograms, and the coefficient of friction is 0.75. Okay, we want to find the minimum magnitude of F needed to slide the block. Okay, and the angle theta for which minimum force will be required. Okay. So, this is not that simple a problem that we are applying a horizontal force. So you can directly see the minimum force required is mu mg to make the block slide. Here we are applying the force at any chosen angle theta. Okay. So according to the value of theta, the amount of force we require will be changing because the normal reaction changes because of F sine theta acting, the vertical component of force. So we have to first of all decide at what angle theta we should apply the force so that the minimum amount of force can be applied to move the block. And based on that angle theta, then we can calculate the magnitude of that minimum force. So just take down and understand the question and we'll discuss next how to solve it. So just assume some general angle theta and start with the free body diagram of the block. Then I'll explain to you how you can minimize the force by manipulating the angle. So start with the free body diagram and find the relationship between F and theta to just about make the block slide. Okay, so let us start this by understanding the free body diagram. So as I said, this is a little bit more complicated than the average situation where you are applying a horizontal force. Here we have to keep in mind that the angle theta can be adjusted according to whatever will be giving us the minimum requirement of force. So you can adjust that angle theta according to requirement. So that is what makes the problem a little bit more complicated mathematically. Anyhow, so let's understand some kind of normal reaction here. Mg, this force F which is acting at an angle theta, and of course there will be friction. So we assume that the body is slipping, then this will be kinetic friction. Okay, because okay. Now we have to find over here minimum value of force for the acceleration to be greater than or just about equal to 0 also when slipping starts. Okay. So now if you break this down to component forces, you'll see that the components of F become F cos theta, F sin theta. Okay. Then we have normal reaction acting vertically upwards. We have mg acting vertically downwards. We have kinetic friction, and that is giving us an acceleration greater than equal to 0. So condition for acceleration to be greater than equal to 0 is that F cos theta should be greater than equal to kinetic friction. Okay. For slipping to just start, okay, the condition is that F cos theta should become equal to mu n. Okay. Now you can also see that normal reaction is mg minus F sin theta. So you substitute this over here. So F cos theta is equal to mu into mg minus F sin theta for friction to just about start. I mean slipping to just about start. Okay. So this equation now has to be solved such that we find the minimum value of F and we find the value of theta for that F to be minimum. Yeah. So hope it is clear up to this point. So now what we have to do next is we have to solve this to find minimum force and theta's value for F to be minimum. This is what we have to do. So it has now converted into a maxima minima problem. As you can see, it has converted into a maxima minima problem. Okay. So further, see this equation will become like this. So you can see here that F has become a function of theta. Okay. So we want to find this one's minima. So this function's minima has to be calculated. You can see this is a function of theta because mu mg is constant. It's only theta which is the variable here. Okay. So this is a function of theta now. This F is a function of theta. for the condition of no slipping. So now all you have to do is calculate the minimum of this function. What is the minimum value of this function? We have to calculate this. So try this out now. Okay, so what is the angle theta for which you are getting this minimum force? Let's just pick up the values again. The coefficient of friction, the mass is 20 kg and the coefficient of friction is 0.75. So what is the angle for which the minimum force will be there? Okay, then we'll check the value. So Tantra is the value of force that you got. That is for how much value of theta? Okay. I'll tell you an easy way to go about calculating the minimum of this. Okay, you can see that we can actually write this as is the denominator, which is the function of theta actually. So instead of writing f itself as a function of theta, we can reduce this further. That way we can just use trigonometry. We don't need to use calculus and maxima minima. Okay, where this function of theta is this. It is cos theta plus mu sine theta, or so that is cos theta plus 3 by 4 sine theta. This is this function. Okay. So therefore we can see f's minimum value will be mu mg divided by this function's maximum value. Okay. So now we have to calculate the maxima of this and the angle theta for which this will be maximum. Both these things we have to calculate. No, not 45 beta. So how we calculate the maximum of this? We will just use trigonometry. Now in trigonometry, you know a choice, you know a simple method that if you have this kind of a function, okay, you can reduce it by using this trick that you multiply with square root of a square plus b square. You know this now? Okay. Then you take this to be cos of some angle, let's say alpha. So this becomes sine of the same angle. So this becomes root of a square plus b square sine theta plus alpha, where alpha is equal to tan inverse of this by this. So b by a. So you can see that y's maxima becomes root of a square plus b square. Okay. For theta plus alpha to be pi by 2, or theta to be pi by 2 minus alpha. This kind of thing we get. So for this theta, the value of this function becomes maximum, which is this. So make use of this. Yes, Tantrish, very good. Okay. So that is what we have to do here. Okay. So we can next express this as square root of this much into sine of theta plus some alpha. So this will become how much now? This will become 5/4. Okay. Where alpha is equal to sine inverse tan inverse b by a. So b is the coefficient of cos theta, e is the coefficient of sine theta. Okay. So this function is basically like this. It is 5/4 sine of theta plus 53 degrees. So we can substitute that back here. So f, which was mu mg upon cos theta plus mu sine theta, this can now be written as mu is, remember, 0.75, but the denominator, this function, we've now reduced this function to this. Okay, so the minimum value of this function will become this much. When sine of theta plus 53 is 1, so that means theta is 37 degrees. So this will correspond to this minimum. So 120 newtons will be the minimum force required to drag this block. It has to be applied at theta equal to 37 degrees with respect to the horizontal. Okay, so make sure you understand how we have applied this trigonometrical equations method to solve this over here. Okay, so this is an important type of example. There is a question like this in HC Verma friction exercise also. So you can do that. Okay, so now we more or less done all the types of problems involved in friction. But one more variation we'll see of the two block problem, okay, is something like this. Now in this situation, we have a combination of three blocks instead of two. It's an extension of the two block problem. But we'll see the method of solving is very much like the two block problem method only. So no need to get too hassled about a problem like this just because it looks like there are a lot of things. Okay, but so let's say between these two blocks, there is a coefficient of friction of 0.2, and between these two blocks, there is a coefficient of friction of 0.6. Okay. And masses are given to us as 1 kg, 2 kg, and 3 kgs like this. Okay. Now suppose what we do is in the first part, a horizontal force of F equal to, let us say, 12 newtons is applied on block B. Okay. So we want to find the accelerations. And in the next part, let's say okay. So we'll use very much the same type of approach that we did for the two blocks, but only we'll have to check friction at two places here. Okay, so just take down the data of the question. I'll explain to you how to do the first part. Then you can try the second part yourself. Okay, so let's take that same type of approach. So for the first part, when we are applying this force to the middle block, So let's first of all try to understand how friction acts between the various blocks. So what is happening is the moment we apply this external force on the block B, the friction between A and B tries to oppose the slipping. So it acts like this. And again, the friction between B and C also opposes slipping. So it acts like this. Okay. And you can see if the vertical forces are taken into consideration. So N1 is equal to the weight of this block, which was 10 newtons. So F1 should be less than equal to mu1 N1. So that will be less than equal to 0.2 into this, so 2 newtons. Similarly, on this, there is vertical force N1, weight of this block, another vertical force N2. So N2 is equal to N1 plus weight of the block B. So that will be 30 newtons. So this friction F2 that is acting, it should be less than equal to mu2 N2. So this should be less than equal to, now this was 0.6. So 0.6 into 30, so 18 newtons. So this is the maximum friction we have between block A and B. This is the maximum friction we have between B and C. And there's no friction on the ground, so we need not look at these vertical forces. Okay. So this is the thing. Now again, we will start with that only, that for F equal to, what was it now? 12 newtons. Okay. Assuming no slipping, that is acceleration of A is equal to acceleration of B, is equal to acceleration of C, equal to some common acceleration A let. Okay. So for combined free body diagram of A plus B plus C, we'll get this. So the acceleration will come out to be the force, which is 12 newtons, divided by the combined mass, which is 1 plus 2 plus 3 kilograms. So we'll get an acceleration of 2 meters per second square. Now for this acceleration, we have to check the condition on friction F1 and F2, because they should not, the required value of friction cannot exceed the available value of friction, which is 2 newtons and 18 newtons respectively. So let's do that next. Okay. So next you substitute this in A's free body diagram, and you will see that F1 is equal to mass of A into this acceleration. So that was 1 into 2. So that is 2 newtons. And this is just about okay, because the maximum friction we have available is 2 newtons. You've seen that above. Okay, so there's no problem with the slipping here. Next, we also apply this to C's free body diagram. In that you can see F2 will be mass of C into A. So F2 required will come out to be mass of C was 3 kilograms and the acceleration common is 2. So we require 6 newtons of friction, and what is available to us much more, up to 18 newtons is available. So this condition is also satisfied. So we are seeing that so this is also correct. Okay. So therefore we understand that for F equal to 12 newtons, the whole system has a combined acceleration. There's no slipping. neither there's slipping between A and B or any slipping between B and C. Okay. So just take this down and apply the same approach now to the second part, where we are applying the force on block C. So second part, we are applying a force of 24 newtons on the block C instead of applying it on B. Yes, very good, Antresh, that's correct. So in the second part, we will see that there is slipping between A and B, but there is no slipping between B and C. So let's come back to this and see. So if we apply the force of 24 newtons on the block C this time, so if we assume common acceleration, okay, assuming no slipping, we'll see that four meters per second square. Okay. But now when we look at the individual blocks, now we can see that on E, friction F1 is acting like this. On B, F1 is acting like this. F2 is acting like this. Whereas on C, like this. Okay. And we had already seen that F1 maximum value was 2 newtons. F2's maximum value was 18 newtons. Okay. So now we can see that for this acceleration of 4 meters per second square, from E's free body diagram, F1 needs to be 4 newtons. Now we can see that this is wrong. It's not possible because the maximum available friction is only 2 newtons. Okay. So therefore, there is slipping between A and B. So once we know there is slipping between A and B, now what we do is we take the next assumption. Now assume no slipping between B and C. So acceleration of B is equal to acceleration of C equal to some A, whereas acceleration of A is different. It's not equal to A. So now our free body diagram will become like this. On A, there is kinetic friction, which is giving it an acceleration like this. Okay. So solving this will give us the acceleration as 2 meters per second square, because coefficient of friction was 0.2. Okay. Whereas for B and C, we can take a combined free body diagram because we are assuming they are moving together. So on this combined free body diagram, there's only one horizontal force. So we have F is equal to this. Okay. So 24 newtons is equal to 5A. So A should come out to be 4.8 meters per second square. Now we have to check friction. So check friction F2. So for that, make the free body diagram of just the upper block, or rather the middle block. So coming back to the free body diagram of B, there is friction F1 equal to 2 newtons acting backwards, and some friction F2, which is static. Okay. Giving it this acceleration A. Remember, this one is a kinetic friction, whereas this one is a static friction. So we'll have the equation that F2 minus F1 is this. Okay. So F2 is unknown friction, but F1 is the known value of 2 newtons. That should be mass of B, which is 2 kg into combined acceleration 4.8. So we can see the required friction here is 9.6 minus 2 or 7.6 newtons. Whereas what was the maximum friction available to us between B and C? You can see it was 18 newtons. Okay. So therefore this assumption now becomes correct. Okay. Oh, sorry, it will be 9.6 plus 2, my mistake. But even then, okay, so it's 11.6 correct. But even then it is within the limit. Okay. So our assumption is still correct. Okay. So therefore, what is happening is that there is no slipping between B and C. So acceleration of B and acceleration of C have a common value of 4.8 meters per second square, and static friction of 11.6 newtons acts between B and C, whereas A slips with respect to B such that acceleration of A becomes 2 meters per second square, and kinetic friction acts between A and B. Okay, so that is the final conclusion. So that is the final conclusion for the second part. So I'll just take you through the whole solution of the second part. Okay. So if you assume common acceleration, that common acceleration would have been 4 meters per second square, but the friction required on A would have been 4 newtons, which is not possible. So you can see that this assumption is failing. Okay. But there is sufficient friction between B and C. So now we can assume this, that there's no slipping between B and C. So they have a combined acceleration A, but acceleration of A is something different. Okay. So with this assumption, we resolve the problem taking B and C as a combined block because they're moving together, but A as a separate object because there is kinetic friction there. And we solve this condition and we see that yes, enough friction is available. Okay. So solving the whole thing, this is what we get finally. Okay, people. So with this, we complete all the concepts of friction. So today we have discussed mostly JEE advanced type of problems, though sometimes in NEET you can get problems of 2 blocks type. 3 blocks is unlikely for NEET level of questions. It's more for JEE advanced. Okay. So finish up with HC Verma of friction and also work on the module questions. Next lecture we will discuss doubts from HC Verma. Okay. Tomorrow we will do some more practice in friction. Okay. But in the meantime, tomorrow we'll do some selected questions from HCV. Yes, you are having a cumulative test. That's why. Cumulative test will have entire friction. Yes. Okay, so we will do some examples from HC Verma and the module tomorrow. Okay. So even if you have not got enough time to go through the entire module question set, try to at least go through HC Verma fully, so that when we discuss some selected problems tomorrow, you are able to follow everything. That's it for today's session, people. Wish you all the best.